Alright, my name's Drew Sheriff, and welcome to Lab 4. The purpose of this lab was to model circuits using a program to explain what is being observed in the real world. So, the introduction to models and details of experiments. So basically we had two main models during this. On the left, we have the first one with two batteries, a voltmeter and ammeter, and two resistors. And on the right, we have one that had a battery, a capacitor, and a light bulb. So for the first one that I was talking about, I had to go around and figure out the differences in voltage between each of the segments. I had to calculate all of the resistances in ohms of the things in the first experiment. The potential difference on the circuit was 3 volts because there's two batteries that are 1.5 volts. When I attach the voltmeter, I alter the circuit. Why doesn't it change the reading? Because the voltmeter shouldn't really have any resistance. In real life it may, but it's a program, so it should be good. For the ammeter, same thing. It shouldn't have resistance. It's not designed to do that. Were my predictions right? Yes, they were. What does the ammeter read when inserted backwards? Same value. Okay, so for the second model, what happens to the light over time? It dims. What happens to the circuit? The current of the circuit stays the same. On the bottom left, I have the time it takes to charge up the capacitor and release the capacitor. On the right, we have experimental RC, which is just -1 over the RC, which is, and that value is found from the graph I made in Excel. And you take the slope and put that under -1, and then you get 6.03 seconds for my value, which is very close to the estimated 6 seconds that's calculated. Main fundamental physical principles in detail: electric force KQQ over R squared, dP/dt, volts is equal to current times resistance, volts is equal to Q value over capacitance, etc. Here's a little preview of the main results. On the top left, we have my little graph that I drew out that was specified to be drawn specifically. I have it drawn out on a whiteboard, and you can see over time how the voltage changes. Then we have some snippets of each of the models, and then we have the graph I made. The system is the circuit in all of these cases, and the surroundings are everything else, which in this case is not that much, but the voltmeter is technically surroundings. Initial conditions are the one resistor is 47 ohms, the other is 100 ohms. Time is going to be 0 at the start. Electrons not yet moving. Capacitor 200 millifarads. Light bulbs were 10, 20, and 30 ohms over the course of this lab. Coding details, there is none for this lab. Similarities and differences between data and model predictions. So on the bottom left, we have the first model, and it was the same as what I predicted. As you go around, shows you the values, and then there's a net 0 in the circuit. It completes the circuit. On the right, we use the battery to fill up the capacitor, and then we release it. On the bottom, that's what shows when you take the battery out and you let the capacitor release. Potential sources of error: inputting values wrong, website glitch, plotting on Excel. What if I were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Okay, well then there would be some resistance because nothing's perfect in the real world. It's not going to be actually 0 resistance. But for the purpose of this lab, it's fine that it has 0 resistance. What's different about a real ammeter? How would it affect the circuits you hooked it up to? Well, as I said, it's going to have some resistance. It's not going to just magically fit in there and change nothing. If I did this lab with real circuit components, it would behave differently because it might not be as exact. In this lab, we have pure copper wire, it's exact. It's on a simulated website. Our light bulb might be dead, the resistor could be burnt out, you never know. A battery in real life, how would this affect it? it would slow down the time. It wouldn't be as fast because it's not going to be an ideal battery. It would take longer, as I said, for the capacitor to reach full charge. This prediction wouldn't be as exact in real life. Measure time difference from the predicted time because things wear down, things don't work as efficiently as they used to be, like batteries or capacitors or resistors.